Thanks a lot. I think by now everyone's awake. Hello. Breaking out of serial execution. For those of you who've been in the talk before this talk, we've been talking about threading and very sort of low-level CPU level scaling. I take this whole notion now to the next step and talk about scaling web applications onto many servers, onto architectures that are significantly bigger than a single CPU with many cores. Why would I be the one to talk about it? I currently, just a moment. Darn. I currently run a little startup called I Want My Name that does domain name registration out of Wellington. We target the global market mainly in the US. I also run a little consulting shop called SpringtimeSoft, and I used to run startups in Europe before I came to New Zealand. The most significant one was probably a domain registrar that we scaled from about 10,000 domains when I started to about 1 million in 5 years. So massive growth, a lot of parallel execution, a lot of servers, a lot of hosting stuff going on, and a lot of growth that deprecates code not in years but in months. So a lot of assumptions that I made didn't hold up over the years, and I'm now at a stage where I think I know roughly what scaling is about in the moment. That doesn't hold up for the next years, I'm pretty sure. But for the moment, it looks roughly like this, how I line it out in that code in a moment. So serial execution. The problem that we have with serial execution is it doesn't scale. We run only as fast as our hardware can get us, and we can't go any faster because how? If it is one execution path, we're exactly limited to that one execution path. This is roughly how just stub code, don't try to run it somewhere. We pass a request, we ask a database for something, we wait for the response, we scale some image and we wait for the response, we call some external API, we wait for the response, and somewhere when we've done all that stuff, we render a page. That's serial execution as it's normally done in web applications in a moment. The problem is someone, your marketing guy, will come to you and tell you, our page rendering times went up and that kills our customer perception on the site, and that kills our revenues, and make that smaller. The problem is, the very same guy told you to call those 1,000 external APIs minutes before. So they don't know what they want, but they know exactly what they don't want, and that's the problem. So how do we deal with that? Interpreted languages, I've talked about that in my previous talk, are normally single-threaded. They have one execution path. There are no background paths. There is no sort of way to just say, let's do this and this and this, and when you're all done, tell me that you're done, and then we go on with our business. So there is no real way to actually kick off multiple processes while you're running through an iterative path in your code base. So we came up with a couple of different approaches to solve that problem. The one that is very prominent is just client sides. We don't want to do it server sides, it's too hard. Let's let it do the client, and we have those wonderful pages that sort of render an empty page, and then something pops up here and pops up here and pops up here and pops up here, and somewhere after a couple of minutes, hopefully probably a couple of seconds, you have a page that's actually rendered. Probably changes the layout 3 or 4 times during that period, but you definitely have that problem no longer on the server side. You have that problem on the client side, and your marketing guy is probably happy-ish. The other way is to do it on a server, which is a bit harder, but brings you a lot further. And the server side is either message queues or Gearman or any of the other ways to actually parallelize tasks on your server, and I'll talk especially about the first one, the message queuing. Let's look briefly why I think that client sides is a really bad idea. Client sides means that you do not one request to render your page, but you do actually 20 requests to render your page. And those 20 page requests are fine as long as your server is not busy. But that day where you get that big blog post, everyone's hammering your page. And your traffic is suddenly 20 times the traffic that you would have with a server-side scaling mechanism. And that is exactly the DDoSing yourself problem. You have a really, really bad customer experience for a lot of customers that hit your page for the first time ever. They don't know anything about you. They want to see a page quickly. So they hit your page and nothing, or an empty site with nothing or really only basic information in it. So in order to avoid the problem that you have, that you DDoS yourself basically, or have a really bad customer experience when you actually need it because it's a lot of traffic that you get that you can't convert otherwise. In order to avoid that, I think client-side scaling is suboptimal at best. Which leaves us with server sides. It's harder, I have to admit, but it's getting you way, way, way further, and I'll talk about why. So if we don't look at scaling whatsoever and just look at large-scale architecture meetings in some corporate business, I don't know how many of you attended it. It's dead boring, and they just throw around all sorts of buzzwords and vendor-specific things that don't make any sense if you don't know all the products. But it basically breaks down to a middleware, something, message buses, pipelines, processing pipelines, things like that, that come in various colors and price tags, and normally are from any one of the big vendors like IBM or Microsoft or what have you, Oracle. They're really, really, really expensive. But if you actually look at what they do, they are nothing else than a glorified, or not even glorified, message queue. So it is really just message queuing that they do, and put beautiful labels and nice graphs around it. So what is actually a message queue? A message queue is, in its basic form, nothing else than a stack and a routing mechanism around the stack, and some server some interface that can push information into that routing mechanism and the stacks, and some interface that can pull that information out again. Probably easier to look at a bit of code. We have some information, we have some routing information, and we have some payload that we want to route to this location. And then we just send it off to the message queue. And a message queue routes it to that very location. And then we have some client code that just looks at the stack at that location in the message queue and processes whatever it gets. So that is a message queue in its very, very basic form. This routing information can become arbitrarily complex if you have better message queues. The whole consumer notion can be way more complex if we talk about how message queues can process messages in terms of if they just process it on a one-to-one basis, or if they fan it out to all the consumers, or if they do some funky stuff. So, but the very basic notion is really just a stack. Stuff gets into the stack, stuff gets read out of the stack, and that's somehow taken care of. That a message is only read once, and all those kind of things that normally trip you up, they are being taken care of. Parallel execution. So if we take our idea from before, that we have this bit of code where we do all sorts of requests, and we wanna speed it up, we can probably do it somehow like that. So we pass something, and then we just fire off a request to our database, and fire off a request to scale the damn image, and call some external APIs, and we don't actually care about any of the responses. We just fire all those requests off. And then at the very last moment, before we render the page, we collect all the answers. Because only there we're actually interested in all that crap. We don't need it before. We don't need to know if that scaling of the avatar actually worked till we actually render the page. So this is just taking all that serial execution and all that synchronous code and chuck it up into pieces where we know we don't need the side effects, we don't need the answers of the database queries until we render the page. We don't need to know any of the crap we do up here until we actually render the page. And that way we can fire off way more information and process it in parallel, and we only have to wait for the slowest one of them. So the slowest one of them is the determining time frame that we need for rendering the page. Asynchronous handling is really just send a request, wait for an answer, but while we wait, do something else. Do something else. And it's very natural. We always do something else while we wait. We don't just sit on our hands. So it is from a personal perspective, something that is very, very natural. It is just our programming approach is currently more, we do something serial because it's easier, because it's how we learned it initially, because it's how we sort of were brought up or so. It's just we have to break out of that and do things more in a human, natural way, and do things in more asynchronous way. So let's look at a couple of implementations of message queues, because that's what we will use to actually do this asynchronous calls. AMQP is currently one of the most popular protocols, in my view, for message queuing. One of the, I think, best implementation is RabbitMQ. It's an Erlang-based server that does a lot of the scaling stuff for you, and does a lot of the redundancy things really, really nicely. It has a really nice routing engine and is really very stable. We didn't have any problems with it in production for pretty much 3 years now. There is an Apache version of an AMQP server which is written in Java, as far as I know, and there is a couple of commercial options, and they are all more or less interoperable. So it should be able to take up one client library, connect it to another server, and it should just work. There is ZeroMQ, which is pretty new. ZeroMQ is a project of one of the guys, but actually the driving force behind the RabbitMQ development. Initially, he sort of went through that whole AMQP consortium thing where they have all the standardization happening, and so AMQP is a really robust standard that has a lot of buy-in from the financial industry, from a lot of the big players in the market. Even Microsoft is in there, I think. But there is Red Hat is part of it as well, as I'm aware, and a couple of other big ones. So there is massive buy-in from big vendors, and at some point it was just too big for him, and he was like, okay, we're doing things way too corporate. I actually want to cut it all down and do it from scratch, but this time real. And he sort of wrote the minimal viable message queue thing. And that is ZeroMQ. ZeroMQ is, in its essence, really just a library that does message queuing, but there's daemons around it, and you can there is ties into pretty much every popular programming language in the meantime. And ZeroMQ is a sort of minimal approach. If you need message queuing on one server or a couple of servers, I wouldn't deploy it onto hundreds of servers, but on a small scale, ZeroMQ is a really, really interesting product. And then there is a couple of Redis-based ones that I think are really, really interesting. Resk is one that was developed by the GitHub guys and is used in GitHub. RestMQ is a new one that has a REST interface into a message queue that is based on Redis. So if you're starting out, look at those two. They look promising. I haven't played with them, but I think they're really good approaches. Let's look at a real world example. How do we actually go from I have my monolithic serial execution web application to I have an actual modular thing that scales very nicely and has asynchronous callbacks? So take a code base and try to figure out where am I calling external APIs, or where am I calling code that is adding a significant amount of time to my page rendering time. Take out everything that can actually happen in parallel and is not essentially front-end representation code. So you try to strip out everything that could run on its own without too much dependencies on your front end, and also the stuff that is really adding time to your page rendering. And then you take that code and put it out of your existing web framework into a little daemon. And that little daemon can talk AMQP or any of the other protocols that you choose for interacting with your message queue. This takes a moment for you to find a nice daemon framework. We have written Daemonize, which is a really nice Perl framework that does all that stuff already. It's on GitHub. But there are many approaches to write little daemons in pretty much every language. PHP is probably an exception, but there is stuff where you can actually execute PHP on a command line, which does daemon-like things. So even there you have choices. So you take that functionality and wrap it into a little daemon. And that daemon connects via AMQP back to your front end. And then you have to write in your front end a collector function. And the collector function sits there and waits for AMQP answers to come in. So you've stripped out the bits that take time and only have a stub function that calls it, but it effectively sends off an AMQP request to your backend daemon. The backend daemon processes it, someone sends back an answer, and the answer lands in the collector function. And they collect the answers at the last possible point and render it. That way, everything happens in parallel. It's even happening in different processes. So you don't have any interference with something that is really CPU intensive and chews up all the CPU in the backend. You can just, we'll get into that in a moment, you can just chuck that on a different machine and then you can scale it that way. So we have now something that we have a front end, we have AMQP in the middle, we have a backend, and we're talking to them. But what about caching? We could actually cache some of that stuff because pretty sure there are questions that come up or requests that come up every now and then, and they're always the same. So we already know the answer because 2 users before, or even the same user on the previous site page already requested that very information. So we can actually cache our answers. And I do it in Redis, but you can use any sort of key value in memory storage engine that does caching. So what you actually do is, before firing off that request to AMQP, you actually fire it off to Redis. Check if you have the answer already. If you have it, don't bother. If you don't, push it into AMQP. And your backend daemons start to respond to the Redis server instead of the AMQP server. So your collector function actually starts to poll Redis instead of AMQP. I'll show you pictures afterwards. The I want my name architecture is heavily based on exactly what I've described in a moment. And this is where we ended up after a couple of years of development and many scalability errors and things that went wrong. But this stuff is pretty stable now since a couple of months already, and we don't have any issues, and it evolved within the last 3 years roughly. This is exactly the workflow that I was describing. We have, for pretty much any given command that we have in the backend, we're actually asking Redis if we have a cached answer that is relevant. If we do, we're just responding back. If we don't, we ask AMQP, we kick off a workflow, maybe, in the backend. Workflows are, I'll discuss it later as well, but workflows are very basic things or steps that wrap a couple of steps into one logic entity that we can call from the front end. And so depending on the complexity of the task, we either ask a specific backend daemon or we ask a workflow daemon to actually kick off a workflow and give us a response. And Redis respond, and then we read the responses from Redis. So right after we kicked off all our AMQP requests, we actually start to loop over a Redis key and just wait till everything is there, and then render the page. So this is roughly how that looks like. We use Perl, I'm sorry for that. We have Catalyst framework in the front. Catalyst asks RabbitMQ. RabbitMQ pushes it into a queue. Of those queues hang Perl and Erlang daemons that actually read this information, or they read workflows out of the CouchDB, where we have our workflow definitions, and then all of them reply back into Redis, and Catalyst reads from Redis again. Does that make sense? Any questions so far? So, the workflow daemon. The workflow daemon is a very basic thing. It does nothing else as take a workflow definition, which is a series of tasks, and it's a simple fall through. We know what we're doing in point 1 to hopefully know what we're doing in point 2. In the moment we have some sort of undefined error stage, we're just breaking up, we're stopping, we're not trying to recover at all. So we end up with a very simple engine that just that you fire a command off and a payload off to, and we try to do our best to actually process it, but if we can't recover, we're giving up. And we have a very easy way of recovering from those giving up points, because we have intended giving up points where we just wait for external callbacks or for any sort of events to happen, or a time-based trigger, things like that, where we can recover that callback, that workflow, and just continue processing it. A typical case for workflow is credit card processing, where you normally fire off a call to a credit card gateway, and then often you get a callback from them to your site that actually tells you, yes, this card is authorized, or yes, the CVC code was okay, or you actually have a fraud case, or stuff like that. And in order to capture that in a nice way in a workflow, we send the request off. So the front end sends a request off via MQP. The first daemon processes it, the next daemon processes it. Someone we actually talk to the gateway, and the gateway comes back with everything's okay so far, but wait for the callback. So we pause the workflow at that stage, persist it into CouchDB, and that daemon is free to do something else in a moment. Because we're waiting, we don't have to keep it hanging there. So somewhere we get the callback via the front end. All the front end does is capture the URL and all the payload and fire off another MQP request into our workflow. Our workflow engine detects the correlation ID, finds the workflow that is already started, continues the workflow, and we get a response on the front end. And that whole stuff works fast enough that we can actually do it while the customer is on the website. So we can do really advanced workflow things in our backend, even in sort of real time, without having a lot of complexity to program all that stuff. If you have to program all the single steps that you do in a monolithic piece of code, it is really hard to get it right because of all the callbacks and the asynchronous way that actually happens already that you have to incorporate into your serial code. And another point is the replies. The replies don't really have to happen because a checkout workflow, for example, is a workflow where we register domains and do credit card transactions and do a logging and do all sorts of stuff. We don't need the customer to wait for it. We just tell the customer, yes, we've taken your request, and get him doing something else on the site instead of having him waiting there for serial code to actually execute and do all those things, and somewhere after half a minute or so tell him, yeah, everything is fine. So the whole workflow engine that we have in the backend to control multiple steps that happen during a single sort of execution command can be very easily represented in the workflow. One very big word of warning. Workflow engines can get really quickly very convoluted, and you can waste millions. I've seen really big corporate projects that wasted a lot of time on consultants to implement really fancy method queues, workflows. It doesn't work. Try to make it as easy as possible. What we do a lot is, especially for workflows that are not responding, like transfers, like a domain transfer is a workflow where nothing happens for days till the transfer is actually coming back from the other registrar and is accepted and all those things. So there is workflows that just stall somewhere. We have views onto our CouchDB that expose all the stalled or all the paused or all the broken workflows, and we have different ways to quickly continue them or recover them or cancel them. And the moment we find a pattern that happens more often, we either fix the code that triggers that pattern, or we write a little daemon that actually processes that problem. So if it happens, we know an easy way to recover it. But this is iterative work as it happens. This is not something you spec out in the beginning and write for 3 months, thousands of lines of code, and then you notice that case never happens. So don't try to be smart. Keep it really, really simple. So let's talk briefly about a couple of side effects that we have from that whole architecture. If you write your backend daemons really, really tiny and small, you can actually scale a backend function onto a single machine, onto a cluster of machines, to get the performance out of exactly that function. So if you have, for example, one function that scales images, you probably want to run it on, I don't know, 5 EC2 images that shut itself up and down and register itself in the server, and all that is already taken care of because you can just bring up an instance, and an AMQP client connects to the AMQP server, and that is the registration done. The moment that's there, it can start processing images, and the moment you don't need it anymore, you shut it down. So you can scale really, really easily on the fly as you actually need the resources. You can scale the backend independently from the front end. It's also very, very important. For example, if you have this big blog post happening about your site, everyone hits the front page, but probably no one goes further. So you only need to have your front page cached well and enough servers that can actually withstand the traffic to actually serve the front page. And the backend is totally unimpressed from it because you don't need it. So you can only scale exactly those resources that you need to scale in order to make the whole thing happen. You can also group CPU and memory intensive processes together and all those kind of things that you have if you have a selection of daemons that you can cluster together. The workflow side effects. Come back to that early startup model. You run a startup and you have a very simplistic idea of what a checkout mechanism could do. It builds a credit card, registers a domain, sends something to the customer, done. When your financial guys come and say, hey, accounting, we should probably somehow track where we make money and where it goes. So you plug in an accounting engine. And all you do is really you write a daemon, and then you write one line in your workflow definition where you say, hey, by the way, if everything went well, send it off to the accounting engine. And that is all you do. You can really do that on the fly. You can add fraud detection on the fly. You can do all sorts of things that you can alter the workflow without restarting anything, without doing anything fancy. Just by adding a couple of lines to your workflows, you can start routing your messages or change your workflow, your backend workflow, significantly without big problems. So, further reading, I've done a talk about the workflow engine previously. It's called RabbitMQ and CouchDB is awesome. It's somewhere on SlideShare and also on my website somewhere. I Want My Name infrastructure is another one that I've done about specifically how our infrastructure is working, and it's also on SlideShare. And that's pretty much it. I hope in time. Yeah. Questions?
Way up the back.
Hello. I'm basically rebuilding a whole web stack in more or less the way you proposed. However, we have a layer on the front which is our web cache, so that would be primarily for the same kind of pages that get rendered over and over again, and we've got a lot. We've got 500,000 documents plus web documents plus all of the dynamic generated stuff.
Yeah.
So we're looking at using Varnish primarily, and that seems to be okay at the moment. Are there any other recommendations for front-end cache, like Varnish, but you know?
Varnish is very, very, very good.
Okay, so the configuration for Varnish is C and fun, and tools for managing that sort of thing. Have you seen anything like configuration management for that?
We use Puppet for pretty much everything.
Okay.
That's all of configuration management I'm aware of. We looked into Chef, looks really good as well, but it's really breaks down to writing a bunch of config files and deploy them automatically. So there is no fancy GUI or anything.
Thank you. Next question.
There probably is a nice management interface for Varnish. I'm just not aware of it. I've never used one.
Now I get to pick on you in public. I just want to go back to one of the early slides about Ajax.
Yeah.
And, you know, the point's well taken that, you know, Ajax is not a cure-all by any stretch of the imagination. But the fact of the matter is there are a whole bunch of other arguments for it, especially when you're talking about rendering complex pages. And I'm just wondering if you can talk a little about ways to mitigate the impact, you know, setting up and breaking down HTTP sessions and things like that. You know, I know they do exist, so I'm just wondering if you can sort of go through.
So first off, Ajax is absolutely fine if you use it in a sheltered environment or in an environment where you can control your page impressions. So the moment you're using it in an unsheltered environment where you can't control your page impressions and you have no way of quickly adding resources to your app server and actually scaling the demand if it arises, only then you're in trouble. But there are a lot of, there is especially one really cool thing that is around for the problem with Ajax requests or client-side scaling. I don't want to go into Ajax requests especially, but client-side scaling can be done, for example, via Socket.io. Socket.io is absolutely cool. Uses WebSockets where it can, uses commit long polling where it can, if it can't use Flash sockets, WebSockets, falls back to Flash sockets if it has to, and as a sort of last resort thing, uses Ajax polling. The advantage you have with that one is a connection setup from your browser to your app server happens exactly once, and after that you have a standing connection where you can push back information to the browser. So you basically have a TCP connection in your browser and you can talk to it. And that gives you a lot of benefits in terms of connection setup, because an Ajax request, that's another nice side effect. An Ajax request takes a couple of milliseconds to actually set up, because you have your browser here, you have your app server somewhere else. A TCP handshake is a three-way handshake. Every HTTP request is actually a three-way handshake, and then you start to push data back. So you actually have a significant lag for every Ajax request you're doing. If you can cut down that lag and in the same time also cut down the number of connections you're actually doing to your app server, you're really off to a good start. So Socket.io is a really interesting thing to look into, and I urge everyone who wants to play with WebSockets, don't do it with plain WebSockets, play with Socket.io. It's an interesting thing.
Can you share with us an example of the workflow CouchDB document? Like what the structure inside is like?
I can, sort of. Let's see. Oh no.
While we're waiting for that, here was the next question. Or
all right, if you can do two things at once. In terms of handling errors, not when you've got long delayed things like DNS, but you're handing off something, but you want the answer pronto. Like in your example, you had a whole bunch of things that you wanted to get the answers to that you'd fed off. What sort of error handling is there? You know, if you've got it's on another machine, there's some sort of network problem, you're just not getting the answer. Do you have? Is it try catch? Is there timeouts?
Timeouts. Yeah. The easiest way to just deal with that is timeouts, because you can't really catch an error. There is the backend. An AMQP connection works in a way that you open up a channel and you push informations into the channel and you close it. There is no RPC. RPC works with opening a second queue that you read the answers from and telling the message that you send in, by the way, respond to that queue. So if you can't read anything out of that queue, there is no answer. So the only way you have to is a timeout. There is some sort of control in the AMQP protocol where you can make sure that the answers that the requests actually processed on the other side. So depending on how you handshake your AMQP message on the consumer side, so on the daemon in the backend, depending on how you handle that one, you can actually tell it something failed or it worked, and that is sent back to the client that's actually asking. But that handshaking can take a while because there may be 500 messages in the queue, so you normally don't want to do that.
So can you set a flag saying these are reliable messages, tell me if they didn't get through?
You can define message queues as reliable or unreliable, and you can define your actual connection that you do as I want to have acknowledges if the message was received or not. And on the consumer side, you can set, so that's all RabbitMQ, sorry. I don't know how much of that spec is implemented in the other AMQP servers. I'm talking about RabbitMQ in a moment. And on the consumer side, you can define if you're auto-acknowledging every message you receive or if you want to manually acknowledge a message that you receive. And what you normally want to do is you want to manually accept it after you've actually processed it. So you sort of read a message off the stack. In that moment where you read it off, it is blocked for every other daemon, so it is basically off the queue. And then you process it, and if your processing worked, you acknowledge the message, and only then it is really off the queue. If you don't acknowledge it for any reasons, like your daemon died or anything like that, or you actually had a database transaction that didn't go through and you had to roll back, you just not acknowledge the message and it automatically goes back into the queue after a timeout. That timeout is configurable again. I try to. I don't have the database on my local machine. I have it on my VM that it's not running. But there is, if you look at SlideShare, where am I? Here. If you look at SlideShare and look for this talk, there is example documents in there, and I'm happy to walk you through if you have any questions. It is a very simplistic approach where you have a worker definition and you have a workflow definition, and the worker definition is nothing else than a queue and a command that you send to the queue, and the workflow definition takes the name of that worker and uses it in its workflow definition. It's really, really simple. I don't have the database on here. I don't even have a similar one. But I'm happy to show you afterwards.
I've got two questions. The original overview diagram that you showed all the major moving bits, could you just give us a quick overlay of the physical deployment? Just sort of from a HA perspective, we can see what components are there when things, fail.
We're currently running 4 front-end VMs. We are currently running 2 Redis caches, 2 RabbitMQ servers, and 2 servers that run backends. And the backends, we have pretty much all, not really all, but nearly all backend daemons running on 2 machines in parallel. So we actually read off. So it can be that a workflow is processed on one box and then on the other box is a second bit and the third bit is happening on the third box again. So that is really just reading out of RabbitMQ from queues, and RabbitMQ automatically makes sure that the message is only processed once. So from an HA perspective, CouchDB, there are two servers as well with multi-master replication, so they just replicate in a circle. And yeah, that's pretty much it.
Okay, the second part was, you mentioned that your web framework is always asking Redis first to see if it's cached. And if it doesn't, then it will initiate the queue to request, then it should come back to the cache. Is the framework then just constantly polling, waiting for the cache to have, or is there some sort of trigger to avoid pulling to death the Redis cache?
You can actually wait on a key in Redis. So you basically connect to it and wait for the key to happen. Okay. And the moment the key is there, you get a response.
So it'll block until it comes back. What about in the case of one of the processing servers is actually lost the connection to CouchDB, there's a network failure or something, in which case the MQ, all the requests are always going to time out because nothing will ever acknowledge. Are you going to then effectively bring your cluster into some sort of death spiral where it will constantly be requesting and nobody is ever able to successfully...
Can happen, but normally it shouldn't. If a RabbitMQ box dies, it's very simple because RabbitMQ holds the queues on both rabbits in sync. One on disk if it's a persistent queue, and the other one in memory, so that you get speed out of it. Or if it is a fire and forget queue where you don't really care about the data, you keep them both in memory. So you have redundancy here. If one of those ones dies, it's really, really simple because they are not registered in here anymore. So they wouldn't get any requests. So all the requests get routed to the still alive box. So that one is self-organizing. The moment that one comes up again, it starts to register its daemons in RabbitMQ again, and they come up and start to process messages.
So the case I'm talking about is not that the daemons have failed. They're still there. They're still registered. But they themselves, they can't complete the process. For example, they can't contact the CouchDB, or they can't contact something. So they in turn have failed. They're still there, ready, accepting requests. They're not going to respond to MQ with a valid response. It will time out, and another request will come through, which in turn will fail because the underlying error is still there. Hence, are we going to go into some sort of death spiral waiting for something that can never succeed?
In that moment, you start to accumulate messages in the queue because we can't acknowledge the queues, we don't acknowledge the tickets anymore. And every daemon would basically, that processes one queue would start to fill up with one message. It can't process it and can't acknowledge it as well. So RabbitMQ would just start queuing all new messages in the queue, which has the same effect. It times out. But our monitoring would pick up a growing queue, and we would get pages and would be made aware of that problem, and would need to fix the underlying problem with, I don't know, external API that doesn't respond anymore, or things like that. So you have to set up monitoring around that stuff. And a growing queue is always, or a rapidly growing queue is always a bad sign.
Got a couple of questions up the back.
How does RabbitMQ compare to Cupid? Do you know of Cupid?
I know of Cupid, but I have never played with it. I'm sorry.
With things like RabbitMQ, it seems great for known processes, so things that are repeatable and done often. In an environment I've got, we get unique jobs that run for a long time, but we do need those results, so we block for a hell of a long time. Can something like a message queue be involved? At the moment we throw it off to a grid, wait for that to come back through there, but is there any way you could see using something like a message queue could assist in that?
Absolutely. So if you have a long-running job that blocks for a long time and you're interested in the responses, it's very... So do you have a web front end to that, or what sort of tasks are you talking? So build tasks probably, or something like that.
Yeah, they're unique tasks that come in, so you might have 1,000 in a day. They're totally different. So we need to throw it on basically to see if you work, and then get a result back. So in that sense, they're unique. There is a web front end, so you can see status, mainly if it's pass, fail, and then go collect the result and set.
So the scenario is basically you have a lot of processes, and they run for a long time, and you're interested in the responses and the status codes that they actually emit. In that case, I would write workers, as many as you can handle physically on the box, to process things off the queue, and just run them in parallel, as many as you can afford. And the last step of every processing is to push the status onto some sort of stack, either Redis or in a database or whatever, and then you actually read the database. Because you don't want to, or you use WebSockets, totally. With WebSockets, you can just have a standing connection to a WebSocket backend and then just push the updates to the WebSocket server, and the WebSocket server would update the website in real time.
Thank you.
Next question.
15, we still have a bit of time. Yeah.
Do you have any interactions between your backend services, between your Erlang and your Perl guys? And if so, is that mediated by your workflow engine, or do you use some other mechanism?
Thanks that you ask. We actually run a sort of generic protocol between all the bits here, which is a JSON object. Couldn't be easier. So we have a specially formatted JSON object that has a header section or a meta section and a data section and a response section. And all we do is pushing JSON objects between daemons. And if we, for some reason, can't process something, we just persist it into CouchDB, which takes JSON objects again. So it is a very natural match, and it is very simple to persist and unpersist stuff into and from CouchDB. And in Erlang and in Perl, we never interact directly. We always interact via RabbitMQ. So all those daemons all read off a queue. And every time we need something else to happen, we just push a message onto the queue. And either that process is waiting for the answer itself, so we do sort of RPC calls via RabbitMQ, or that call is just pausing and it's a workflow that is actually pushed around in circles or pushed around in various parts. So we're always talking serialized JSON objects.
So just to clarify, the responses don't go back through RabbitMQ?
Most of them don't. If we do a direct request for something that we know it can't be cached, and we know the workflow name for it, or we know the outcome sort of is really very, very specific to exactly that process, we can tell it to respond directly. So basically one of the fields in the meta section is cached or not. And if the request is cached, the daemon knows, send it to Redis. If the cache flag is not set, send it back to RabbitMQ. And that way we can control on a per message basis if we want to have a direct response or if we want to have a cache response.
So on the front end, you've got two instances of the Rabbit client, one as a publisher, one as a consumer.
Yes. Catalyst is a long-running process, so the first thing Catalyst does is sets up a connection to RabbitMQ, and RabbitMQ does multiplexing for connections. So you have a connection set up once, and then you have so-called channels that multiplex connections within one TCP connection, so that you don't have the overhead of a TCP connection setting up and all those kind of things. And then via that one, we just set up a response channel per request, basically.
Okay, well, it's just about lunchtime, so we'll call the end of the questions there. So thank you very much, Lenz, for a very clear and concise talk.
Thanks.
And the Linux conference would like to present you with a small glass and gold penguin as a memento of this occasion in your talk. Thank you very much.
Thanks.